Can we get a vice president 2 minutes before I forget who's here? Be Don or Dave or who else? Minutes before I forget. What you're going to do, Dave? Thank you. Appreciate it. So, welcome everybody. You have found your way into the University of Lowbrow Astronomers monthly meeting. Since I do see a new face here, I'll do a little intro. I'm Charlie Nielsen, the president of the group. You'll meet some of the other officers that might have reports after when we get to the business part of the meeting. But we're a group of, we'll find out from Doug, I'm guessing about 131 now members?
128.
128. Oh man, we're heading downhill. Or I was wrong. At any rate, as is tradition, we always have our guest speakers speak first, and that way if anybody dared to want to leave after and not miss the business meeting, we might give them that opportunity. So with that, I would normally do an introduction of our guest speaker. However, I'm going to actually introduce the introducer of our speaker, who is our webmaster, Krishna Rao.
Hello.
Take it away.
So it's my pleasure to introduce Dr. Ethan Siegel. Ethan's an astrophysicist, blogger, and podcaster extraordinaire, and a communicator of science to the public. He currently writes the NASA Space Place column, which many of us read regularly. He has a blog, Starts with the Bang, which is one of the best I've ever read at communicating complex scientific topics in just plain English. And as a reminder, he has a book out called Beyond the Galaxy, How Humanity Looked Beyond Our Milky Way and Discovered the Entire Universe. I think, Ethan, this is the part where you're supposed to plug your book and hold it up in front of the camera.
Okay. I'm going to plug my book and hold it up in front of the camera. So this is a book, Beyond the Galaxy, and it is on sale wherever fine books are sold, including at Amazon, where it's probably the easiest to get. And yeah, if anyone wants an autographed copy, just contact me offline, and you'll have to pay for shipping, and I will send you one.
And I said this last time, but this is still true. My favorite review, looking on the Amazon reviews, is that this is the first page turner to contain Meson diagrams that they ever read. So Ethan did his undergraduate studies at Northwestern University and went on to earn his PhD in physics from the University of Florida. This was followed by a master's degree. His thesis advisor was Dr. Pamela Gay, someone who most people in this room know from her own public outreach work, and she gave a talk to our club a few years back. And his Google profile states he is also a competitive beardsman. And I'm not entirely sure how a beard competition would go, but I'm pretty sure he'd win.
Boston Red Sox usually talented.
Is that right? So, of course, his most prestigious honor was that he gave us a talk about the gravitational wave discovery early this past year. But now he's back to talk about the original topic, which was New Horizons, Pluto, and the outer solar system. So please join me in welcoming Ethan.
So one of the great things is when you want to talk about something in space and you schedule it, and then it's many months until you actually give the talk, you realize, oh my God, the thing that I was going to talk about is now not sufficient because so many new things have happened ever since then. And so I was originally, what I told Krishna I was going to talk about is, oh, New Horizons has just happened. Do you want me to talk about the solar system beyond Neptune? And he was like, yeah, that'd be a great topic. And then the gravitational wave discovery happened, and so we talked about that instead. Then this came along, and in the meantime, since we've had New Horizons and the flyby of Pluto, and it started returning all of the wonderful images, we've learned so much more than we have since I was originally going to talk to you guys in February. It's now 8 months later, and what's happened? Well, one of the things you have to realize is when you fly from the inner solar system all the way out to where Pluto is, that's a long journey for sure, right? If you were going to say, well, how long does it take a light signal to get there? The answer is a little over 4 hours. It's around 5 hours now for light to travel from Pluto to Earth. But what that means is if you are this tiny little satellite broadcasting all the data you took, right? This thing flew by Pluto. It's got pretty state-of-the-art equipment and cameras and instruments on it, taking all of this data in all these different ways, in all these different frequencies, etc. And you want to send it back to Earth. I can't send it the same way I send my voice to you. I need to send everything together with this incredibly powerful antenna. And you know how things spread out over time. Even a laser that would be incredibly well collimated, it would spread out like a cone over distance. This is how that is kind of forced to work. So what happens when you spread out over this great distance? You're going to wind up seeing, oh, this is actually relatively bad. The farther and farther away I get, the bigger a dish or the bigger an antenna or the bigger a collecting device I need. Because even these radio photons that I'm sending out with all of this data embedded in it, they spread out over such a great distance and such a great time that by the time they get to Earth, there were really only a handful of gigantic radio dishes capable of gathering this information. So to be broadcasting its data that it accumulated when it flew by Pluto in July of last year at full power. It's transmitting this at full power. And you say, well, if we try and download this data to the best of our abilities, how long does it take? Well, the answer is it takes about 16 months. And that's with tricks of compression and boosting power and taking other systems offline that New Horizons is able to do. So today we take a look and say, well, what did we wind up with? And the answer is, for New Horizons, now we finally have almost all of the data. So we've got the full planet data, and a lot of it was really surprising because we also have small strips that were imaged in ultra high resolution, right? You can't see the full planet because New Horizons flew by so fast that all it could do was get the side of Pluto that was lit up by the sun at that time, at the time of the flyby. Pluto rotates on its axis, pardon me, and it has a pretty fast day, but New Horizons only made that close approach and was moving so quickly that there was very little it could do. There was very little it could do as far as seeing, well, where is everything going to be? So we really got that one hemisphere, and then we flew by into the shadow of Pluto to get a good image of its atmosphere. So we got the one side that was lit up that had that big heart-shaped feature. And on the illuminated side, we were able to find a huge number of outstanding things. We were able to find, first off, that Pluto is not what we originally thought of as this cold, distant, inactive, frozen world. We kind of expected that we would find, like, oh, it's just this big ball of ice. It's like the ice version of an asteroid. And Pluto's not like that at all. It is not just this heavily cratered mess of ice, you know, at 40-something Kelvin, which is the temperature you'd expect, being so far away from the sun. Instead, what it is it's this world with this huge diversity of geology on it. It has ice mountains that extend a mile in altitude. It has these plains with pits in them, and it has almost no visible craters at all. So we get this huge variety of terrain, and we see that this terrain is changing over time. And we also see, all of this is a surprise because we've never been to a world out this far before. We finally get to this point, and what we're seeing is not a uniform world at all, not something that's evidence of an old surface, but something that has no craters, so it's evidence of a newly surfaced world that also has this big diversity of features. So what's going on there? Well, one key that we got is from the night side of Pluto, because when New Horizons flew by Pluto, right, if the sun is shining over on one side, then Pluto's going to have a shadow cone behind it. Just like Earth has a shadow cone that the moon passes through and we get a lunar eclipse, Pluto has a shadow cone. And what New Horizons was selected to do was to fly behind Pluto and into that shadow cone. So what it could see just like you could see if you were on the surface of the moon during a lunar eclipse, was you'd be able to see Earth's atmosphere illuminated by the sun. People were able to see Pluto's atmosphere, including the clouds and the hazes and everything you'd want to be there, illuminated by the sun. So we were able to determine how thick Pluto's atmosphere is. It's much thinner than we thought it was going to be. We were able to see whether it has clouds and what those clouds are made of. And yes, it does have clouds. And the clouds, interestingly enough, are made of a number of different things, including methane. Methane hazes and clouds, similar to what you might expect on Saturn's moon Titan. But what's amazing about this is we have precipitation as well. Now, we didn't see active precipitation. We just saw evidence of precipitation on Pluto. But what we see on the surface and what we've learned from the atmosphere is that Pluto has 3 types of ices covering its surface. It has methane ice, it has water ice, and it has nitrogen ice. And these are of different densities. So where you have these mountains, that's water ice floating on a sea of solid nitrogen. Where you have those plains on Pluto, what they call Sputnik planum, is this flat area that gets pits in it. That's mostly solid nitrogen. It's so cold out by Pluto that liquid nitrogen, which has a freezing point of 77 Kelvin, no, it's colder than that. That's when it boils. But it's solid at whatever temperature nitrogen becomes a solid at. And that's what we see on Pluto, is it has solids there. And those pits are evidence of sublimation, where you get on the day side, things go from solid into gas. That's what's happening in those flat areas. And so we can see this varied and interesting geology on Pluto. What's weird about this is when we look at Charon, Pluto's moon, it doesn't have any of that. Charon doesn't have ice mountains. It doesn't have these liquid surfaces. It doesn't have precipitation, and it does have craters on the surface. So whatever's responsible for this active ice geology and these weather cycles on Pluto that's keeping its surface young, that's not happening on Charon. It makes you wonder, what's going on here? Is this because it's a binary system that's close together and the more massive one gets all the atmosphere and the less massive one just loses all its atmosphere? Is it something like actually they both lose their atmosphere, but Pluto can hold on to some and Charon can't hold on to any? Is it more like, you need to be a certain mass and a certain size to hang on to all of this stuff, and Pluto can do it, but Charon can't, which means if we go to Eris, we'll see Eris is like Pluto, but if we go to a smaller world like Quaoar or Makemake, we'll see, nope, those are like Charon. This is really interesting because this is our first time out there. We like to have this idea that we know what we're doing, and that when you see a certain member of a class of objects, you're getting something that's representative of this class of objects. We didn't know very much about the Kuiper Belt very recently. We think like Pluto, that's old. That's been part of the solar system for a long time. We discovered it in 1929, 1930. It's been around a long, long, long time, right? Well, the way we discovered it was from what's called a blink comparator, which is an old tool where basically you would take a snapshot of a part of the sky, and then you'd wait a bit, and then you'd take a snapshot of that same part of the sky, and you'd take a look at all the stars and all the fixed objects, and you'd match them up, and you'd subtract them out, and you'd look for anything that moved. Now, we used to do this visually. It was called a blink comparator because you'd look at one image with one eye, and you'd look at the other image with the other eye. Is you'd say, well, would this work? Is what I see with my left eye the same as what I see with my right eye? I know it looks like I'm lifting the wrong ones up, but I promise we're flipped. So that's what you do, is you say, okay, well, That's what I do with my blink comparator. We can do this all digitally now. But we discovered Pluto in 1930, and we kept looking for more distant objects, for more objects out this far, because the theory said that, well, when the solar system formed, you should get these planets, right? In the inner part of the solar system, some will be rocky and some will be gas giants, right around where you hit the temperature where it was cool enough that ice, liquid water, would freeze into ice all the time. That should be what you call the frost line. And so you should get this collection of frozen rocky bodies there. That's the asteroid belt. And then out beyond the last gas giant, you should have more planetoids, planetesimals, small icy bodies that couldn't coalesce and form a planet on their own. And that's what the Kuiper Belt is. Now, asteroids, we've known a ton of them since the early 1800s. The very first, some of you may remember, oh, Pluto used to be a planet and then it wasn't, and that caused a big uproar. Well, way before Pluto was ever discovered, in 1801, there was this Italian guy, Giuseppe Piazzi. He discovered, he said it was an object between Mars and Jupiter. And he said, it's kind of like a comet, except it doesn't have a tail and it doesn't have any nebulosity and it doesn't have a coma. So I have a suspicion that it might be something better than a comet. And he writes this, and then he goes, but I have been careful to keep this supposition to myself. Because you don't want to get everyone's hopes up. You don't want to get everyone's hopes that, oh, what's happening is, yeah, we've got a comet here, or no, we've got a planet here, and then have it turn out not to be a planet. Well, in 1801, he discovered the first, asteroid. By 1810, we had like maybe a dozen of them, and by 1850, we had hundreds. So we realized pretty quickly that asteroids weren't, we have this one and it's a planet. We realized, oh no, like there's a whole slew of these objects. We thought when we discovered Pluto that there would be a whole slew of these objects coming as well. But Pluto discovered in 1930, if you say, when did we get the second Kuiper Belt object? It didn't happen for 48 years. It didn't happen until 1978. And the second Kuiper Belt object was Charon, was Pluto's giant moon. We didn't discover the first object not in the Pluto system that was beyond Neptune until 1992. Yet over the last 25 years, we've gotten amazing at it, not only from Hubble and from infrared telescopes, but from ground-based telescopes too. And we've wound up discovering over 1,000 of these objects out beyond Neptune. And so when you go to Pluto, you think that what you're going to find is representative of everything else that's out there. But you fly by Pluto, you fly by Charon because it's the same system, and you discover that even these first two worlds are nothing like each other. And so this is bizarre, this is a puzzle, but this is also incredibly interesting because we're learning that there may be even more diversity between Kuiper Belt objects than there is diversity between the different planets in our solar system. So this is really an amazing advance. This is an amazing find, and we're only starting to uncover the geological history and story of Pluto and of all objects in the Kuiper Belt. We are today as far as what we got from going to Pluto and what we've learned from that one flyby. Now, New Horizons is on to the next target already. It got approved, and it's going to start observing a target that it couldn't have been sent to when it was launched 10 years ago now, because this target was only discovered by Hubble in 2014. And so this object that it's going to observe next is going to be much smaller than Pluto. It will likely be icy, but will it have weather? Will it have craters? We don't know. This is part of the learning endeavor, is we saw one and it was different than we expected. And when we looked at Charon, we said, well, now we have Pluto and now we have Charon, and they're different from each other. So what else is out there? These objects have a big diversity from what we can tell. Some are redder, some are bluer. Some orbit roughly in a circular orbit outside of Neptune. Some are inclined to the solar system's plane, and some are really, really inclined. And some are very ellipsoidal in their orbits. Some of them really, seem to come interior to others, and some go much farther out. Pluto, in fact, used to be, at least it was when I was born, Pluto was interior to Neptune and only transitioned to being outside back in the late 20th century. Many of these orbits are not as circular as the planets, and so we're really on the cusp of discovering a whole lot more about the outer solar system, which may turn out to be more interesting than anything we found in the inner solar system. There was something else. There's a lot to talk about Pluto, and although I'm not an expert on it, I'll be happy to take questions on it when we're done with the talk part. But something I'd also like to talk about is there's been a lot of talk this year about a new idea that's come out by Mike Brown and Konstantin Batygin, who are two planetary scientists, also in the outer solar system, also out beyond Neptune. But this is way beyond Neptune. They put out a new hypothesis that even though Pluto isn't the 9th planet, because there are other objects around as massive as it, because there are other objects that meet the same criteria Pluto does that fail to meet planetary status, but there may be a true 9th planet way, way out there beyond Neptune, maybe 40 times as distant from the sun as Neptune is. So Neptune, to put it in perspective, if you took a look at what are the ratios of Venus's distance from the sun to Neptune's distance from the sun, that's about a factor of 40. If you said, okay, that's how far Neptune's orbit is, and Neptune's orbit is pretty far, right? It's about 30 astronomical units away from the sun, and it takes about 165 years for Neptune to make one orbit around the sun. So you're looking at about 10 to 20,000 astronomical units. Is that right? No, that's too many. You're looking at an orbital period of tens of thousands of years, and you're looking at an object that might be as many as 200 or 300 or 400 astronomical units away from the sun. So you're talking about something that's massive, that's way far out there, and that could be doing something that we haven't seen anything else do before. One of the puzzles we've learned about our solar system is we have these rocky worlds, right? We have Mercury, Venus, Earth, and Mars, and we have the asteroids and the Kuiper Belt objects, and then we have the gas giants, but we don't have anything in between. We don't have any super Earths, or we don't have any mini Neptunes. We don't have any planets that are between about 2 Earth masses and about 10 Earth masses. And this turns out to be the most common type of planet in the universe, which we've learned from the Kepler mission and the study of exoplanets. And so this is a little bit of a puzzle. Where are the super Earths? Where are the mini Neptunes? And why don't we have one in the solar system? Well, the idea of Planet 9 is that maybe we do. Maybe we do have one, and it's just super far away. That's what this object would be. Now, the whole reason this object was first hypothesized was because if you take a look at the Kuiper Belt objects, the objects beyond Neptune, they fall into a few different categories. You have the objects that are like Pluto, which are redder. You have the bluer ones. You have the ones in the scattered disk. You have the ones in the actual Kuiper Belt itself. You have the very, very long period comets, which are thought to have originated maybe from the inner Oort cloud and been perturbed. But then what you have is you have a few objects that do something weird, that orbit in this weird super long period ellipse where The closest approach brings them sort of to where the Kuiper Belt is, but the farthest approach takes them not hundreds, but thousands or tens of thousands of astronomical units away from the sun. You have these really elliptical orbits, and you find them inclined at all these weird inclinations to the solar system's plane. And what's even more than that is you can plot, okay, everything has an ecliptic latitude and an ecliptic longitude, right? That's just you make a map of the sky, you say, where is the perihelion? That's the closest approach to the sun. Where's the aphelion? That's the furthest approach from the sun. And we have a handful of these weird, long period, very elliptical objects. And so you decide to plot these in ecliptic latitude and ecliptic longitude. And what you find is all of them are incredibly tightly clustered, that there's less than a 1 in 100 chance of them all having the same narrow latitudes. And there's less than a 1 in 100 chance of them having all the same narrow longitudes. So if you put that together, then you find there's less than a 1 in 10,000 chance that these, at the time the paper was written, that these 6 objects would have the properties that they do. So when something is very unlikely to happen by random chance and it happens anyway, one of the things you do as a scientist is you say, well, could there be a cause to this? What are the things that could cause this? And one of the options, one of the things that could cause it is, well, what if there were this massive body inclined to the plane of the solar system that were moving a very large distance away from the sun? What would its mass have to be? What would its orbital parameters have to be for it to cause these long period objects to be correlated like this? And what else would it predict? Well, we said, well, there should be more objects that should look like this. There should be a massive planet that looks like this. And roughly here's the region of space where it would be. And so since that time, we've discovered additional long period outer Kuiper Belt objects that seem to have this close approach to the sun that takes them near to the Kuiper Belt, that should have their aphelion, their farthest approach from the sun, be these thousands of times further away. And we can plot, what's your ecliptic latitude? What's your ecliptic longitude? And again, it's clustered in those same narrow regions. So things are pretty consistent there. Then you can say, well, we want to look for this planet. So we go to look for this world, and where do we look? And the answer is, well, we've got a pretty nicely constrained space, but it's going to take years to do the full survey. So we haven't found it yet. And of course, that's what you do, is if you find this world, then that's the game, and this world exists, and that's pretty amazing. You have to remember that this wouldn't be the first time that was done. We found Uranus, right? The inner planets, Saturn and inner, you can see with the naked eye, so you've known about those since ancient times. Uranus we found serendipitously in 1781. William Herschel was looking through his telescope and he found this weird little blue disk, and that turned out to be Uranus. So great. What did they do? They said, here, William Herschel, have a ton of money and have a ton of telescopes, and now you can go build the world's largest telescope and live the rest of your life being very, very happy as an astronomer. And he did, and his kids did, and it was fantastic. The story is a little different. To discover Neptune, they were actually looking at the fact that Uranus's orbit didn't obey Kepler's laws of motion, right? Kepler's laws of motion were from the early 1600s. This was stuff. So if in the 1800s you couldn't obey the laws of planetary motion that, now we know we can derive from Newton's gravity, but you couldn't obey these laws of planetary motion that had been around for hundreds of years, what's wrong? Well, what was wrong was Uranus started to move too quickly for Kepler's second law. And then it started to move at the right speed, and then it slowed down and was moving too slowly. So again, what could be causing this? Well, maybe the laws of physics were wrong, or maybe if this were Uranus going around, maybe there was another more massive planet out beyond it that was tugging on Uranus as they orbited, and so it caused it to look like it was moving faster. And then when Uranus overtakes it, would be in the direction of your line of sight, so you couldn't see it moving faster or slower. But once Uranus passes it and it tugs Uranus backwards, it causes it to slow down. So from Earth, you should see this planet moving more slowly. Well, we had enough data by the mid-1800s that you could, if you had this idea, you could calculate where would that planet have to be, what would its mass have to be, and where could you find it today? And they did that. The person who did the calculation correctly was Urbain Le Verrier. He was a French guy in 1846. He did this calculation. He wrote a letter about, here's where it is. I'll send it to the observatory in Berlin. Go look for this. They got the letter in Berlin. They looked for it that night, and less than 1 degree from where Le Verrier predicted it was, there it was. So we've discovered worlds before based on their gravitational influence. Just earlier this week, a new study came out where they said, if you have a massive planet, something maybe 10 times the Earth's mass, orbiting this far away over 4.5 billion years, what are the things it could cause? Well, remember, this is the plane of our solar system. If this object is orbiting inclined, severely inclined to the solar system, what it's going to do is it's going to cause over time the plane that your solar system's planets orbit in, it's going to cause it to tilt relative to the rotation of the sun. You'd expect when you form a solar system that everything spins in the same way, that the sun should spin in the same way, that the planets form in a plane and all the planets should spin the same way, and things might get perturbed because, you know, physics is messy and things collide and all of that. But when we look at our sun and how it spins, and we look at the planets and the plane they orbit in, it's off by about 7 degrees. And there's some uncertainty there because some of the planets are off by only like 5 degrees, and some of the planets are off by like 8 degrees. So I'll say 7 degrees, but there's a little bit of wiggle room. But you would expect to things, if they're going to be off by like a few degrees, that they'd all be off by different amounts, as opposed to just all the planets orbit in this plane and there's a little bit of wiggle room, but that whole plane is tilted. Well, it turns out if you have a massive planet orbiting out of that plane farther out, it's going to cause over billions of years your solar system's orbital plane to tilt a little bit relative to your sun. So this has been a mystery ever since we first discovered that the sun rotates and it doesn't rotate in the exact same plane that the planets orbit in. And we could finally have an explanation for that. Now, I'm actually on record on the internet as being super skeptical of Planet 9, of I'm the one who's like, well, what about these alternative explanations? And what about these other things? And what if we don't find them? And what if we haven't found them yet? But the beauty of science is open to all of these different possibilities. And whatever you can imagine is going to be proven right or wrong dependent on what we observe. So the key is now we're going to keep looking for these long period objects and see if they keep correlating in latitude and longitude. We're going to keep running simulations of the solar system and try and pin down if that is the explanation for why the planets are tilted relative to the sun's rotation, why we're going to see things do whatever they do. We're going to try and say, well, where should that planet be? But ideally, over the next decade, some people are more optimistic and say over the next 3 years, but let's give them more time. Either find this planet or not. And if you find it, then maybe we need to reconsider what our definition of a planet is. Maybe we need to consider that if you have something more massive than Earth, even if it's far enough out that it doesn't clear its orbit, maybe if it has the right mass to orbital distance, semi-major axis distance that we need, maybe that's what we should use as our definition of a planet. The nice thing about that is if we use that definition of a planet, we can start applying it to other solar systems without having to figure out whether they've cleared their orbits or not. So that's really a short synopsis of what we've learned about the solar system out beyond Neptune and where we are today and what some of those cutting edge things we're looking to discover beyond, well, here's Pluto and what we saw and what we learned about it, and here's Charon and what we learned and what we saw about it, and here are all these objects orbiting the way they orbit, and that's some data. Like, that's an amazing part of the story. That's an amazing story that we've really only started to uncover over the last 24, 25 years. We've come a tremendous amount of distance in that. Like, I'm kind of in awe of it because this was like a pipe dream when I was a kid. Like, yeah, we know there's Pluto and maybe there's other stuff, but we don't know. And now we know, and we know of thousands of these objects. It's estimated that there are as many as 200,000 Kuiper Belt objects that are as large as, you know, the small moons we have in the solar system. So there's a whole lot to discover out there. And this may eventually teach us about the transition from the Kuiper Belt, where things are collimated into sort of a disk, versus the inner Oort cloud, where things are expected to be more spheroidal. So we're really just stepping out beyond the planets in our solar system, and yet there are surprises out there, including potentially a new planet. Now, the last time I spoke to your club, you had a whole lot of questions for me, including about what I talked about, but also a number of things that I didn't talk about. And so I plan to talk to you guys today for a little bit less than an hour, so maybe only 40 minutes, so that I have time to take all the questions that you came up with. So now that we've talked a little bit about Pluto and about New Horizons and also about Planet 9 and what we've been looking at with that, what questions do you have, and what else would you like to know?
Yeah.
There we go.
That's over.
Okay.
There we go.
Okay. Assuming that there is a Planet 9, would the James Webb Telescope be able to spot it easily in IR?
Okay, so this is a really good question, right? So assuming that there is a Planet 9, could you look for it in the infrared? So James Webb Space Telescope is going to be great for imaging things that we know already exist, right? So if you're saying, hey, I've got this great telescope, it's great in the infrared, and just for people who haven't followed your line of reasoning, which is completely correct, the way planets work is they get their energy from two things. One is reflected sunlight. So yeah, if the sun hits an object, light bounces off, you can see that, and that's in the optical. But also, objects absorb light or emit their own internal heat, and that puts them in the infrared. If you had infrared eyes where instead of seeing like 300 Kelvin, you could see half of that, you would see Jupiter shine like it was a star undergoing fusion, because Jupiter generates so much of its own internal heat, so much more than it actually absorbs from the sun, or radiates from the sun, that Jupiter would shine in the infrared from its own internal light. So you say, well, if we have a planet out, you know, super far from the solar system center, that it might not be able to reflect sunlight very well, but couldn't it still be of a hot enough temperature that we'd see it in the infrared? Well, yes, but James Webb is not a wide field telescope. So if you say, well, I've narrowed it down and Planet 9 is somewhere in this region of the sky, it's going to take you millennia to find it with the James Webb Space Telescope. So James Webb isn't the right tool to look for it. In fact, we do have all-sky infrared surveys. We had WISE. Spitzer did a great job doing the galactic plane. So we do have infrared observatories some of which likewise have covered the entire sky. And so because we haven't seen anything that would be Planet 9 in those surveys, we've been able to say, well, if there is a Planet 9, it can't be more massive than about Saturn. So that's because the smaller mass you get, the less infrared emission you get. So it can't be bigger than about Saturn. So Saturn, no. Jupiter, no. But if you have a Neptune-sized object or a smaller than Neptune-sized object, we're not sensitive to that yet. So our best bet, ironically, is to go look with something like the Gemini telescope, which is like an 8 to 10 meter class optical telescope, and try and look for the reflected light. It has this combination of, large aperture, good seeing, and also wide field viewing. That's going to be the best way to discover it. Once you find it, image it with James Webb. You're going to learn a ton about it. That's probably a fantastic tool for doing exactly that. But for that, it's not the best tool for discovery. It's the best tool for follow-up observations.
Thank you.
Thank you.
More questions for Ethan? Wow, no. Well, see, you said we had a lot of questions, and now we don't.
So I thought
I know. I think I jinxed it. How did I? I'm sorry, guys. I should have prepared more. I know you have more. Maybe you just need a little more confidence, or I can ask myself one if you don't really have.
We just came up with.
Yeah, we've got two more. We've got one in the front row here.
Okay, great.
you may have covered this during the talk, but have other planets been discovered in other worlds about as far away as this Planet 9 would be from our own sun? Do we have any examples of that in other solar systems?
Oh, yeah, we do. But they're not going to be the ones you want. So there are a few different ways we have of detecting objects that are in other solar systems. And I'm going to just give you three of them. One of them is the transit method. So if you have a star that is way distant from you and you're looking at it, if you have a planet that transits in front of that star relative to your line of sight, it's going to block some of that light as it passes in front of the star's disk. And if it does that periodically, if you see it dims and it dims and it dims, then you can say, all right, I got it. I know that I think that there's a planet there. But if something's very far away, you're not going to be able to get multiple transits on that time scale. It would take you tens of thousands of years. So that's a great way for finding planets, but not those types of planets. You can also look at the stellar wobble method, which you don't need a perfect alignment. You just need for a planet to be massive enough that orbits a star. The star feels the gravitational pull of the planet, so it makes an orbit also. So you can say, well, I'm going to look for the wobbling of the star. But again, if something is super far away and takes a long time to orbit, you're only going to be able to see the ones that orbit close enough in. Or again, you have to watch for tens of thousands of years. But we do have the prospect of direct imaging. Things are well enough separated. If two objects are separated by enough, then what we can do is we can say, oh, I can actually see there's separate things here. And we've been able to image planets that are that far from their star. But the planets we've been able to image are bright enough that at least in the infrared, they can emit enough light that we can detect them directly from a space telescope. So the answer is yes, we have detected planets as far away from their star as Planet 9 is, and in fact, those are common. But we've never detected a planet that far from its sun that's as low in mass as a Planet 9 is. We've only been able to detect planets that are many times the mass of Jupiter that are that distant from their sun. So that doesn't mean they're not out there, but that means as far as our technology has been able to do to the present day, that's the best we've been able to see. That was also a really good question.
You said we might be able to detect it in visible light, what would the magnitude be, the estimated magnitude in visible light of Planet 9?
So was the question, what's the estimated visual magnitude of Planet 9 in visible light?
Yes.
Okay, let's see. So let me do a little bit of math because I haven't been asked that before. So the way magnitudes work is I only know how to do it comparatively. So if you assume it's going to be similar to Pluto, right, this thing is about 30 times as far as Pluto. So 30 times as far means 1/900th the light. And then it's going to be larger than Pluto. If it's 10 times the mass of Earth, then it's going to be roughly about 2 to 3 times the physical diameter of Earth. And Earth itself is about 4 times the diameter of Pluto. So let's call that 15 times as much. So you're basically saying this is going to be 1/60th as bright as Pluto. And then if you're turning that into magnitudes, because a factor of 2.5 is about a magnitude, then that's, let's see, 2.5, 6-ish. It's probably going to be about 5 magnitudes, 4.5 to 5 magnitudes fainter than Pluto is astronomically. So whatever the visual magnitude of Pluto is, you need to see to about 4 or 5 magnitudes fainter.
That's about minus 19, I think. Yeah.
Oh, man.
That would be about minus 19. I was at the Star Party, and the fellow was looking for Quoar with his 32, and he found it. And I think it's dimmer than that.
Well, great. The problem is you need to know what you're looking for, and so that means you can't look at it and be like, oh, I see that dot there, I know what that is. There are lots of very faint dots in the night sky that haven't been well cataloged. But you know, if you wanted to say the vast region of sky, the many square degrees where it could be, and I want to image it deeply, and I want to do it like tonight, and then I want to do it like 3 nights from now, and I want to see if anything's moved. That's the concept. That's the exact concept in astronomy. So if you wanted to do that yourself and you could go faint enough to do it, why not? It's reflected light. So I would say go for it. If you beat the Gemini telescope to the punch, like you're the you're the coolest astronomer since Jim Christie discovered Charon.
Yeah.
Any other questions?
So I've got a question for you, Ethan.
Yeah.
So shifting to the really outer portions of the solar system, meaning to a different solar system, we've heard a lot about Proxima Centauri lately, and how the planet there is in what could be considered the habitable zone. I don't know if you want to talk a little bit about what you think about that planet and what the prospects are of actually having potentially some sort of life there.
Okay, sure. So we talked about 3 methods, right? We talked about direct imaging, we talked about the transit method, and we talked about the stellar wobble method. And the way we found Proxima B is what it's called, was from the wobble method. That was what the scientists at European Southern Observatory were using, is they were measuring the wobble of this star over time. So wobble, just to be clear, is not if I were to look directly at the star, wobble is not seeing the star go side to side. So it does that, we're not sensitive enough to see that. Wobble instead is seeing a star move velocity-wise away from you and have its light red shifted and then towards you and be blue shifted. So what we saw is this periodic back and forth motion of the star relative to our line of sight. And based on that, you don't know whether the planet orbits. So here's the star and here's the planet. So if the planet's orbiting like this, you don't know whether the planet is of a certain mass and it's orbiting this way, whether the planet is tilted and is more massive, or is severely tilted and is much more massive. So what we can do for that is we can put a minimum mass, which is to say, if the alignment is very, very good, what's the mass of this planet? And therefore, what's the size? And the answer is the mass is about 130% the mass of Earth, which means it should be physically only about 10% bigger and therefore should be rocky. Now, Proxima Centauri, the star, is very, very dim compared to our star. It has about 12% of the mass, which is really only a little bit over the threshold, the 8% of our sun threshold, for actually being a star. If you're below that, you can't undergo nuclear fusion in your core. So Proxima Centauri is only about, I'll say it's about 12% the mass of our sun, which means it's only about 0.1 or 0.2% the brightness of our sun. And almost all of that light is in the infrared. So it's only about 1/10,000th as bright as our sun in visible light. Because of its orbital properties, right, it's very close in to its star, right? In order to get enough light and heat so that, I mean, part of the reason we're interested on it is it's at the right conditions, that if it has an Earth-like atmosphere, it's at the right temperature to have liquid water on its surface. It gets about 70% of the energy from the sun, from its sun, that we get from ours at its distance. But that means its day is very fast. It makes a complete year, once about every 11 days of our Earth days. It doesn't have days on it because given Proxima B's mass, given the mass of this planet, and given their orbital size, this world would become tidally locked to its star the way the same face of the moon always faces us wherever it is in its orbit. It would become tidally locked in the span of just a few thousand years, in less than 1 million years. And Proxima Centauri, from our estimates, is billions of years old. So therefore, this planet's going to be really weird. It's going to have a hot side that always faces its sun. It's going to have a frozen side where it's always night, never sees the sun. And then it's going to have this ring around it, which is a nice temperate zone, which we might want to consider colonizing, or, you know, at least looking for liquid water or similar life to what we understand life is going to be like. But it's really interesting because the star that Proxima b is means that any life that is on this world is probably going to be really different to life on our world. We're used to ultraviolet light is what you use to ionize atoms. And Proxima b, by virtue of where its spectrum is and what its stellar temperature is, emits almost no ultraviolet light. In fact, it emits almost no violet or blue or cyan light. The light doesn't really start to pick up until you get into the yellows or reds, and then it peaks deep in the infrared. And so if you're starting to look at the molecules that like plants use on Earth, well, we have 2 chlorophyll molecules, chlorophyll A and chlorophyll B, that plants take advantage of. One of them won't work on Proxima b because there isn't enough of the blue light for that to work. So plants wouldn't be green. In fact, something that grew up on Proxima b would probably look at humans and be like, oh, you guys see way into the ultraviolet and we see visible light, but their visible light will correspond to our infrared light. Because when we look out at stars, there are a bunch of stars that are cooler in temperature than ours are, and those appear red, and the ones that are hotter in temperature appear blue, and the ones that are about the same temperature appear white to our eyes. To someone who lived on Proxima b, astronomy would be really different. Some of the stars would be white, but most of the stars would be super blue because that's it. Every other star is pretty much of a higher temperature than theirs. And what's also weird is the brightest stars in our sky are, Sirius, which is maybe 8.6 light years away and is of magnitude for you astronomers about -1, -1.5, somewhere around there. And we have a few stars of that same magnitude. Proxima Centauri is very close to Alpha Centauri A and Alpha Centauri B. It's less than about 0.2 light years away from them. So to someone who lived on Proxima B, Centauri A and Alpha Centauri B would be separated by about this much on the sky, and each one of them would be brighter than Venus appears at its brightest. Because Proxima B, or Proxima Centauri, is so much fainter than our sun is, it's pretty much guaranteed that anyone living on Proxima B would be able to see Alpha Centauri A and B both day or night. So no matter where you were on that world, if you had a view of a sky that included Alpha Centauri A and Alpha Centauri B, you'd be able to see them no matter when it was or where you were. So I think that this is a really interesting world by virtue of the fact that it's also a world around the star closest to the sun in the galaxy right now, and also that it's a potentially habitable rocky world with maybe liquid water on it. This is the no-brainer first world beyond our solar system that if we wanted to explore it or probe it or send something there, this is the place to go. You might make the case like, well, I like the one around Tau Ceti better, and I would say, good for you. Go explore the thing that's 2.5 times far away. So after we go to Proxima Centauri and come back and go back there again, then you can tell me how things are doing over on Tau Ceti.
Anything else?
Well, if no one else has one, I do have one more question.
Right.
So just to go to another recent news item, apparently it was more than a rounding error. There aren't 100 billion galaxies in the visible universe, but something on the order of 1 trillion or more. And
Yes.
so I've seen a lot of reporting about this and how just, marveling over how incredible that is and how vast that is. But what I wonder, how does that influence our knowledge of cosmologic evolution? I mean, if we're off by that much, does that mean there's more matter in the universe than we anticipated? Does that have implications for how some of the models of the universe evolving over the course of what we see starting at the cosmic microwave background to now? Does that change anything like that, or is it really just there's more stuff there and that's it?
What if I told you neither of those? You tend to think like, okay, when you say there are this many galaxies in the universe, that you're actually making an estimate for how many galaxies there are in the universe. And what if I told you that's not what we've ever done? When we say how many galaxies are there in the universe, what we've been doing is we've been actually measuring there are at least this many galaxies in the universe, and we don't have a good estimate. So the way we've been calculating this is we've been doing something like we've been doing since the early 1990s, where we started measuring things like the Hubble Deep Field, where you say, okay, this is the first time we're doing this. It's 1994. We just put the fixed mirror on the Hubble Space Telescope, and now we can finally see stuff, and it's amazing. What do I want to do? Well, I'm going to be really ambitious, and so instead of looking at like an observing target where there's like a star or a galaxy or a nebula or an object of interest to image, I want to find a region of sky that has absolutely nothing of interest to image. So I want to find something that has super nothing in it. Nothing. No stars, no galaxies, no known anything. And I want to image that. And I want to image that for days. I want to take this multi-billion-dollar space telescope where everyone is clamoring for observing time, and I want to monopolize it to look at nothing. That's what I want to do. you can imagine there was a lot of pushback the first time this was proposed. Because what if you see nothing, right? What if you go and you look into the deep abyss of the universe, and either because there's nothing there to see, or because your instruments aren't good enough to see it because you don't know what you're looking at, what if you see nothing? What if you legitimately don't see anything at all? So they did this, and the first time they did this, they did the equivalent of 9 days worth of observing in a few different visible light filters, and they pointed it at a region of sky that had nothing in it. And what came back were, okay, we'll take an image, and we'll image it for about 40 minutes, and we'll collect a photon and another photon and another photon. And then, we have to close the shutter because we orbit on the other side of Earth. And then we come back and we're going to open it again and we're going to take another image. And they stacked 341 of those 40-minute images, and they put it all together, and they got the Hubble Deep Field out. And what they found were about 3,000 galaxies in this tiny little region of space. And so what you could do is you could say, well, I'm going to take the region of space that we observed. I'm going to calculate how many of these regions would it take to fill up the sky. And then I'm going to multiply that by the number of galaxies we found, and that's my estimate. Now, every time we've taken a better image, when we went from the Hubble Deep Field to the Hubble Ultra Deep Field to the Hubble Extreme Deep Field, we've increased that number. The last image that we had, the Hubble Extreme Deep Field, was released in 2012. It covered a region of the sky that was 1/32 millionth of the sky. And it had 5,500 galaxies in it, which means if you multiply those numbers together, you get approximately 170 billion galaxies in the universe. But that's a lower limit. And one of the reasons this is a lower limit and not likely to be the true number is when you look out into the universe, you're basically making a cone. So I'm drawing you a two-dimensional slice of a cone that looks like a V, because your field of view is going to see a certain amount of sky up close, and then as you go further away, in order to cover the same amount, right? So if you start up close, you're like, I'm covering this much. Then as you go further away, if you want to keep that relatively the same size, you're going to get bigger and bigger volumes of space. So close by, you find, yes, I can observe the bright galaxies and the faint galaxies, and I count them and I see them. And as I go further away, I'm getting bigger volumes of space. And you start to see more bright galaxies, and you start to see more faint galaxies, bigger numbers of faint galaxies, but you're probably not seeing them all, because the very faintest ones, the ones that you can barely see up close, they're now far enough away that you can't see them very well anymore, or maybe at all anymore, that you would need a bigger telescope or more observing time in order to be able to see them. But there are more of them because at a more distant time in the past, you had more numbers of small galaxies that are still merging together to form bigger ones today. What we see is that these galaxies do evolve, that if you go all the way back to the Big Bang, the only galaxies you can see are the brightest and smallest ones. Smallest because only the small ones are around back then. The most distant galaxies we've seen only have maybe 1 or 2 or 3 billion stars in them, less than 1% of what we find in the Milky Way or Andromeda, because they just haven't had enough time to form stars. So you have this scenario where galaxies merge together over time and become bigger and bigger. We know right now in our local group, we have the Milky Way and Andromeda as our 2 really big galaxies. We also have other significant ones. We have the Triangulum Galaxy, the Large and Small Magellanic Clouds, and some others. And then we have a bunch of dwarf galaxies, maybe as many as 50, 60, or even more, that we're still turning up. But we know in another few billion years, maybe 10 billion years, maybe 20 billion years, we're only going to have one galaxy in the local group. It's going to be this giant elliptical galaxy where everything's going to fall in together. The Milky Way and Andromeda are going to merge about 4 billion years from now, and in 7 billion years we'll have an elliptical. Triangulum will probably fall in shortly after, and eventually all the other dwarf galaxies will come in too. So the number of galaxies in the universe is going down. But as we look farther and farther away, we're able to see fewer and fewer of the galaxies that are there. So if you said there's 170 billion galaxies in the universe, based on what we've seen, you have a really good idea that what you've seen is not representative of what's there. The big advance in saying there are 2 trillion galaxies is for the first time they've been able to put quantitative distances on all the galaxies, not just in like one small thing like the Hubble Extreme Deep Field, but across many of the fields in the Hubble Frontier Fields program, which has a very wide field of view, which has, you know, many hundreds of times the viewing area of like the Hubble Extreme Deep Field. So you have a larger sample, you have a good understanding now of structure formation in our universe, including with dark matter and baryons and acoustic oscillations and all the different things you need to reproduce the large scale structure in the universe. You have a good idea from intermediate redshifts and from near redshifts what small satellite galaxies and dwarf galaxies look like. And so finally, for the first time, you're able to say, well, extrapolating over the whole universe and over the universe's entire cosmic history, knowing we're looking 1, 2, 3, 5, 10, 14 billion years back into the past, how many total galaxies are there within the observable universe? And that's where the 2 trillion number comes from. Hubble hasn't seen most of these. We've still only seen around 10% of them in the richest region of space. We just know here are the ones that we calculate to be there, and yes, they should be beyond the viewing limits of what Hubble has seen in those images. But this is something that James Webb will be able to see. This is something that the next generation of 30-meter ground-based telescopes is going to open up the universe's eyes on for us. And this is something when we do go to the infrared, we'll be able to see these colossally redshifted galaxies. So it's not that this changes the amount of dark matter in there. In fact, knowing the amount of dark matter was really important to coming up with that number. And it's not a case of, oh, we just discovered all these galaxies that we didn't know were there. No, we determined that these are the galaxies that need to be there. And now we hope to go and see them. I'm sorry, I feel like that could have been a whole talk in itself. I'm sorry if that was long.
No, thank you. That was great.
Okay, your last chance. Any other questions for Ethan? Okay, seeing none, I think we're finally done with you. At long last. Thanks for your time. We appreciate it.
All right, well, thank you for having me. It's my pleasure as always, and I will stop the broadcast and let you get to the rest of your meeting. Thank you for having me, and we'll have to do it again sometime. I'm sure there will be new discoveries to talk about.
You bet.
Definitely. Thanks, Ethan.
Thank you. Bye, everyone.